Again. So what I'm going to do today, I will pass through a sequence of different methods for solving nonlinear equations in one variable. Some of them are variants of the, like in Newton methods, a variant of the fixed point method, but some very special and useful variants, and some of them are not, and it will be clear. So essentially, I would like to give a reasoning behind this method, so you see how they are formed. I will give one of the proofs. So for the Newton method, I will give you a complete proof, so you see how it can be made in the rigorous form. In general, it's very unlikely, unless you will do this exercise, very unlikely that you will have to implement methods, this kind of methods numerically, because they're already implemented in many programs, like in MATLAB. They're already available. And often when you use the solver and you see the description, like in help, so there are some extra parameters you can pass to the solver, for example, choosing what method to use. In MATLAB, often you can just write a parameter, set a method, use, and tell the use this specific method. So it's good to have some idea of what the methods are, and probably one of the method that people use a lot is the Newton's method, or some variants of the Newton methods. So Newton's method, often called with the two names, Newton-Raphson. Raphson method. So what we will do, we'll look for solutions of nonlinear equation. So for now, we just consider one variable. And what the Newton method does, it's just fixed point method but for special function that is constructed using f. So take g of x as x minus f of x, f prime of x. Correct. Yeah. So what you see? So if f of x has a solution and at point f, at point x, and the derivative at this point is non-zero, then it's clearly then automatically x is fixed point of j. So what we do is we use fixed point method. So fixed point method, it means just iterate this function j, which tells you that each next iteration, x plus 1, should be computed as j of the previous iteration. And this is exactly what is Newton method. So this is one of the ways to derive this method. Another way how it is. So this is because we already know that there is a fixed point method, but you can just derive this method directly. So another derivation So take Taylor expansion. Okay, so take the function of f or at any point. So we want to so having an approximation at certain iteration xk. So we solve the equation 0 equal f of x, right? But now expand this expression at this point. So it will be f of xk plus f prime of xk x minus xk plus so on. So whenever square and so on. So whenever your approximation is good, so if approximation is close to the solution, so every next term is smaller. So that's the idea of Taylor approximation. So every next term is smaller. So this part is small. So assuming that this part is small, you can write that this is approximately this. So it's 0. And then you approximate new x. So then that means that x is approximately so we have divide and put to the other side. Minus. No. So this is a new formula, and this gives you better approximation. So this is what's called xk plus 1, and this is Newton method. So we derived it in a sense from a Taylor series, taking into account that we just have the first derivative. And this reasoning allows to give you a geometric understanding of this method. So it will be f, function of x. Then we have a function. This is our function f. This is our solution, x. So what the method does, so you take having some approximation of the solution xk. So what you do, you substitute a function, you see, by its linear approximation at the function k, point xk. So what means that you truncate the Taylor series means that you just take Taylor series at this point and just take linear part. That means that it's straight line which is tangent to the graph at that point. This will be straight line. So this is linear approximation, and then for you find 0 for the linear approximation, which means that the point where it intersects the 0 line. And this gives you next x k plus 1. Yeah? And then you do the next step is just the same way. So you take this point and take the linear approximation, and then you go to the next iteration. So you see it converges, it looks to converge rather fast. So the good part is that what we'll see, it has a quadratic convergence in general. there will be theorem about this. At the same time, it's not. There is a problem of the method, or Newton method, used directly because it converges very, very well when the initial guess is good. So if you start sufficiently close to the solution, it will converge very, very fast. But if you don't start near the solution, then the situation can be much worse. So for example, if you have this function like this, and you want to find this solution, and you put a guess, well, if you start here, well, you see, you will converge, right? So from this point. But if you start from this point already, it will go like just go to a different place. And if you start it from this point, it will just go in just opposite direction. So it's not if you don't start near the not sufficiently close to the root, then you can have some difficulties with the convergence. For example, it can diverge to infinity or whatever can happen. So that quadratic convergence, but in general, if you start close enough. Okay. So if you start close enough, then everything works. So theorem, which we can prove, it's about convergence, existence, and uniqueness, right? Convergence, existence. So theorem tells the following. So consider interval. Consider an interval on a line and a function which will be in C2. C2. So twice differentiable, continuously differentiable functions. With the properties. So this is already tells you the class of functions for which we will have nice properties. So we see for this theorem, the conclusion of this theorem, especially the conclusion about quadratic convergence, it implies that there are two derivatives. So if the function has two derivatives, so it's sufficiently good, then you use Newton method. If it's non-differentiable, for example, or just continuous, or just one, or has one derivative, there is no big point of. Maybe there is no big point of using Newton method. Let me use different thing. So with properties, the properties will be the following. So we have a derivative bounded from below in absolute value. So derivative is non-zero. And the second derivative is bounded from above. For some positive, so for x from interval, and some given positive numbers m0, m small and m capital. So it's for every x and for given two numbers. So we have this function. So then we can, in this case, we can tell the following. So let x be the root, be the solution. And define the new interval, which will be interval centered at x with a size with any size which is smaller than, bigger than 0 and smaller than 2m over m capital. So everything is constructive. So assume that you have a solution and you give the interval around this point, which is which has a size defined in terms of this estimate. So this has to do about starting sufficiently close. Yeah. So not too far, not too far. So then we have the following things. So first, that this interval contains a unique solution, x. So there are no other solutions. So so this interval, there will be no other solution. So this will be good. So if you start close enough, we go to that solution, not to the other one. And the second, for each initial condition from this interval, the Newton method converges to x. With the estimates, and then we can give estimates which particularly tell you that this is a quadratic convergence. So there will be three different estimates. So first estimate is that the distance from the solution will decrease at least as well. There will be a prefactor, just a constant, and then there will be q in the power 2 in the power k. So there will be, you see, so it's double exponential quantity, where q is again the same prefactor, just flipped by the initial distance. So this is how fast we will approach the solution. And this is, I'll make computers, this is quite fast, because this is number in the power, right? And you see that this is smaller than 1, right? So this is smaller than 1 because x is taken from, is not distance between x and a, or distance between x0 and x taken from this interval is smaller than term over m, and that's multiplied by m over 2m, so it's smaller than 1. So it's a number smaller than 1 in the power 2 in the power k. So this goes very fast. Where k equals 10, it will be this number in power 1000, more or less, 1024. Okay, so the next estimate, so there are just several estimates like this, so which can be used in different forms. So another estimate that tell that this is smaller or equal than 1 over m of function f at this point, which is itself because of the smaller or equal than m over 2m square. Okay. And C is that xk plus 1 minus x is smaller or equal than m, so over to m. So some constant by xk minus x squared. So these are similar in the spirit. So we show that the next iteration is bounded by the square of the previous iteration, right? In different ways. And this is mean that the rate is quadratic. Yeah, so every next step, you go as a square. You decrease you're getting closer as a square of the previous step. So now I will show how to prove this theorem, because one theorem we will prove, and then the other theorems I'll leave you to read in book to see how it's done. So theorems are important because they guarantee when it converges. It tells you what is important for the convergence, right? So the first, second derivatives give you some estimates which guarantee, like how far you have to start, or you can start, and what is influencing this distance, and so on. So certainly, in general, you can use and see if it converges or not, right? But if it does not, then you can start thinking what was wrong, and the theorem helps. Okay, so we will prove. So the proof is actually rather straightforward. It is using essentially the Taylor series. So let's start with the lemma. So first, for every 2 points, we have f of y equal f of, now let's go make it. So which one was good? Let's write it for x, the way around. Let's see. Doesn't matter. So y so I'm writing the Taylor series, but the last term will be, the second order term will be exact. Where this term is a second order term, but now we put the factor which gives you exact equality. So it's integral 1 minus s f double prime y. Okay, so they're just formula. It's a formula which is kind of three-term Taylor series where the second term is multiplied not just by the second derivative, but you see by some kind of averaged and integrated second derivative, some form of average second derivative in the interval. So the proof. Okay, so proof is the following. So this expression is true for x equal y. Yeah, that's correct, no? Because when x equal y, it's 0 equals 0. So fx equal fy. This is correct. So then in the second we fix x. Yeah, let's fix x. No, let's fix y. And take derivative with respect to x. So take derivative with respect to x from both sides. So what you have? Prime of x equal prime of will be correct. Go in a way how it is done. So first let's start with the proof of lemma. First check that f of x equal f of y plus f prime of y, x minus y, plus integral from y to x, minus t prime of t dt. Okay, so this we can prove, and this is can be proven by just differentiation with respect to x, right? So you see, in order to prove, you can check that this is true for x equal y, and then you can check that derivative is 0. And that's enough. So this is how you check it. And then what you do is you take a change of variables. So set s equal t minus x over t minus y over x minus y. So s new integration variable. So what do you have? In that case, t equal, from this expression you can express t, it will be s of x minus y plus y. And dt, which is here, will be x minus y ds. So we make this change of variables. So whenever you do it, so the first part is the same. And then the limits, so when you set t equal y at 0, so if one is 0, another will be 1. X minus t will be this, right? So it will be x minus t will be s minus, so x minus t. You see it will give 1 minus s by y minus 6. X minus t minus s. So this is x minus t. And then it will be f prime, f double prime. And then there will be dt, which is x minus y ds. And you see that this is exactly the two terms, which is x minus y. They can be put outside the interval. No, that's essentially exactly this expression. So the idea of this derivation is, in order to make it gives you exact expression of f in terms of differences and in terms of derivatives which we can bound. So now we can prove this theorem. So what you do, first we start with just inequality, the difference of the values divided by difference of the arguments. Well, it's equal to, we know that it's always equal to the derivative somewhere in between. So this is mean value theorem. And this is bounded by condition, so it's bigger than or equal than m. And this is for any 2 points. So from this, you can just rearranging this, so it's m x minus y should be smaller or equal than difference. Okay, so this is first step. So the second step, we use lemma. What we can do is, what did I write? Yeah, what we can do is that we can, what we will need, we will approximate this expression that we will use. Essentially, this expression. So let's put y here. So we know that this is, we just put all other terms to the other side. So it will be f of x minus f of y, and plot this r function, minus this r function. So minus, it's okay, no? Yeah, it's okay. X minus 1 square by the interval 1 minus s f double prime. Doesn't matter what is inside because we will use an estimate. So this is small or equal. So we can take a triangle inequality just for this difference and separately computing the other difference. So it will be small or equal than f of x minus f of y. And this part plus absolute value of this part, but we know that second derivative is bounded by m, right? Is bounded by m, and integral is 1/2. Okay? So it's plus m over 2 x minus y squared. So we have this inequality. And now using this inequality, we will show that there is a convergence by using this theorem for the convergence of the fixed point method. So what we need to show that our function j, that let's remember what is j. Let's see. Two steps. First step, let's show uniqueness first. Uniqueness. In the interval so first show the uniqueness. How we show uniqueness is assuming the contrary. That is another solution. In this same interval. So what we have? So if we assume that it's another solution, we can just use this expression. So we have an absolute value of f prime of what? Of nu. So we take, we don't need, we can write y here, just having another, so we don't need to change our notations. So we have this by x minus y. And this is bounded by this. So it's small or equal then. squared, but this is 0 because they're both solutions. We assume that x and y are both solutions, so this is 0. And now we can cancel 1 minus, so since x, we assume that x is not y, we can cancel one of the terms. So what will be left is f prime y is smaller or equal than m big and x minus y in absolute value. But this is but this is small. This is both x and y are in the same interval. So this is the difference between x and y is not bigger than a. And a, we know that it's smaller than 2m over m than m. And this is contradiction. Remember that f prime should be bigger than or equal than m by the condition. So it should be bigger or equal, but we showed that if there are two solutions, then the derivative should be smaller. So there is a contradiction. So it means that the solution is unique. So in this interval. So we proved the uniqueness of the solution. So next we prove convergence. So convergence. So convergence we prove using the fixed point method. So we use this function j of y equal, let's say j of x equal x minus f of x over f prime of x. And we know that Newton method is just fixed point method for this function. So what we can just prove the conditions. We can prove the conditions of the theorem and use theorem for fixed point method. So we have to prove two things. Essentially, we have to prove that this is contraction. In this interval. So we have to prove that J is a contraction of this interval. So we have to prove first that it maps interval inside the interval, and the second we have to prove that it contracts. So the distance between points getting smaller. I'm not good. I'll go to the first part. Let me see. I think I don't need any more. Yeah. Lemma we don't need anymore. So let's just compute. So let's compute so take y from point from this interval, and so we need to show that gy is also from this interval. Which means that, or which is the same, is that g of y minus x is smaller or equal than a. So this is what we need to show. So okay, so let's just compute directly this quantity. So let's remember what is J. J is y minus f y prime of y minus x. And this can be rewritten as, let's put f prime in the denominator. So what will be left? So from here it will be just f. And and this term will give you plus, just put minus, so it will be x minus y f prime. And now remember that this was already present in our lemma. So with once again we use lemma. So this will be minus. So this is exactly r xy with a minus. Remember that f of x is 0. So take this formula, so this will be r. So this gives you r xy over f prime of y. And now put a modulus everywhere. And now remember how we did the estimate. So R, we remember we know how to estimate because R is, we already estimated it as m over 2 by x minus y squared. So this is what we already did last time. And then f prime is bigger than m, the small m, but it's in denominator, so it's still the same inequality. So we can put m here. It goes well. And this is now this is smaller than or equal than a. So this is smaller or equal than m over 2m a squared. And this is bigger than a. No, this is smaller than 1 over a. So this continues to be smaller than a. That's it. So this is exactly what we wanted to prove. Yeah. So we proved that it maps interval to an interval. And the next step is we need to show that there is a so the next step we need to show that it's contracting, but in fact what you can do is you show that it's contracting, but you already directly show that it's converging. So actually, I think it's good for you to see how you directly reduce it to the previous theorem, but actually how the proof is given is just direct. The direct proof that there is convergence. So take y equal xk, then j of y will be sk plus 1. This is by definition of the Newton method. So what do you have? xk plus 1. So exactly this inequality. So let's rewrite it. It is smaller or equal than this part. And this part is xk minus x squared. And unfortunately, this is exactly what is proving this C, which I unfortunately erased. So this is exactly the estimate showing the quadratic convergence. So already by showing that it maps interval to itself, it's enough. It brings us enough information to prove that it's converging and that the convergence is quadratic. Okay, so we already have C. The next is to prove other two inequalities. So how we do it? Much time. I don't want to spend all the time with the proof, so I think that it's essentially enough. So by doing a bit more job, you prove A and B, and I'll just put it for you for the exercise. A and B. You can check the book. So look how you can prove the rest. So the proofs are usually rather elementary, as you can see. There is not much mathematical complexity in the proof. It's essentially the basic analysis on the line. So that you just have to arrange in a clever way so you come to the result. So that we prove that so essentially with Newton method, we prove that having some estimates on having two derivatives first, having estimates on the first and second derivative, for the first from below, from the second derivative from above, we can guarantee that in the interval of certain size around the solution, there are no other solutions. The method is converging, and the method converges also quadratically. So everything works very nicely. And let us just put two observations. So first observation. So first observation is how fast is quadratic convergence. And the good example is you just have an example. So let's just take certain numbers. So you see Q is a certain number smaller than 1. So let's take this number even not too close, too small. So let's take Q equal 0.9. That's what we'll put here, 0.9. So actually not close at all to the solution, but within the interval. And let's take also to m over m. Let's take order 1, just normal situation. Okay, so after, and we make 10 iterations of the Newton method. Just 10 times iterate. So remember, if you iterate 10 times with bisection method, so you can only come to error like 0.001. So what will be error with the Newton method is it will be smaller or equal than to m over m, q in the power 2 in the power 10. So this is 2m over m q. So this is something, it's exactly 2024. So this is approximately 10 power minus 47. So just with, if you have very precise calculation with enough digits, like with 50 digits, so after just 10 iterations, you're already as precise as 10 minus 50. So the quadratic convergence is fast. And the fact that it's this quadratic convergence, you can also see directly from the fixed point algorithm. So if you take, remember, so that our function j, like x, no? Was x minus f of x, f prime of x. And we had a theorem that was telling that if at the fixed point j is 0 and certain derivatives are 0, then the method converges not linearly but with a higher order. So let's just check that this is true. So if f of x is 0, so first of all, automatically we have that this is fixed point, right? So which was the idea why we Newton method comes from a fixed point algorithm, because 0, it implied that it's fixed point of j, so we can just use a fixed point algorithm with j. But now it's not only this. So we can compute derivative of x at the point, at the solution. So derivative will be, so it will be 1 minus, when you derive f prime of x over f prime of x, and then you take derivative of the denominator. F. Like this, correct? And you see that this is 0, right? Because 1 and minus 1, and this is also 0 because f is 0. So this is 0. So now if you compute the next derivative, you will see that it's not 0. Let's check. So the q is the first derivative which is not 0, is 2. And this means that it's a quadratic convergence. So check the theorem from the previous class. In the previous class, we showed that if as a fixed point algorithm, also some derivatives up till the order q are 0, then there is it's convergence over the q, and we get it that it's convergence of order 2. So this is already, we know from direct proof, but you can see it also from previous theorems. Let's make a very short break, just take coffee, and I will explain you a couple of more methods, just to relax before. Coffee, and I'll be back. 2 minutes. Okay. So, there are plenty of other methods, so I will pass through some of them, essentially giving you an idea what are the reasons. So one of the second method will, second method. So the second method will be the second with A. So second method is kind of in the spirit of Newton method, but it is used when we do not have derivative. So the Newton method requires derivatives. Derivatives sometimes it's hard to get. For example, in practical problem, you want to minimize the weight of the plane with respect to some parameters. So it probably takes a lot of computational effort to compute just weight. But imagine that you compute derivative. So derivative, maybe it's even impossible to get. But derivative still, even if you cannot compute directly derivative, you can estimate the derivative from the finite difference. So essentially, this is an idea. So we approximate derivative from two previous steps. Because we already have these steps. So it's almost cost nothing to take the difference. Right? So this is approximation of the derivative. And then you use this derivative instead of, use this expression instead of the derivative in the Newton method. And then you get this, and then you get what it's called second method. So you use this expression. So what's the difference? Now you see that every next step depends on the two previous steps. Yeah? So the first difference is that you need initialization with 2 points. So if Newton methods, you should just give x0. Here you have to give 2 points with which you start, and then you go. And the second point, and this is not a fixed point method. This is because you see, fixed point method is that it can be reduced to fixed point method if it's a function of the previous step. But you see, it's a function of two previous steps. So it's not already the method, fixed point method as a Newton method, and we can write draw the geometric interpretation. So if you put a function f, this is our function f. This is our solution. So what the method does is that you take 2 points, xk minus 1. Then assume that this is xk. So remember that Newton method was obtained by substituting the function by its linear approximation at the previous point with a derivative at this point. And now we, instead of derivative, we approximate derivative as a straight line between the two previous points. So essentially what we do, we draw a straight line through two previous points. So this is exactly what is done, and find the way it intersects 0. So this gives you xk. So xk minus plus 1. So this is the second method. Second method means that in the Newton method, you would take just tangent and go closer. In the second, you don't have derivatives, so you cannot put tangent, so you pass a line for 2 previous points and see where it comes. And you already see that it's certainly slower, it has a slower convergence as the Newton method, because the Newton method would get a slightly better line. So there is a theorem. I will put a theorem without a proof. So the theorem is assume that some interval contains a zero of a function f, which will be twice differentiable, and that there is an estimate. So m, which will be maximum in this interval of second derivatives divided by twice minimum in the interval of the first derivatives. And assume that it's bigger than bigger than 0 means how it can be. Well, you check the proof, but I think this just means that the minimum is not 0. Okay. So let consider two first points from the interval, which, as we did before, is an interval around the solution with the same a, which is with a is delta over m, and delta is smaller than 1. So essentially, it's the same idea. Actually, it's just written. I took it from a book. It's just written. It's actually almost the same expression that we had for Newton method, but just written it in different form. Because there we had estimate for minimum, estimate for maximum. You can check it. It's similar. So then iterates that you obtained from the second method of the second method converge to the solution with the arrow, and this is interesting. So the arrow is bounded by 1 over m delta, and here you have sigma k. Instead of 2, you have sigma, and sigma is golden mean. So you have a golden mean coming out. So the order of the method, the rate of convergence, let's say rate of convergence is golden mean. 1.6. So for the proof, see the book. See how the golden mean can appear. Okay. So the next method that you can do just in the same way, but slightly more advanced, so is taking, so you took 2 points and approximated the third. So you can do it with more points. So you take this is our solution. So this is f, this is x, and this is the solution we want to find. So assume that you've got you remember 3 points. xk minus 2, xk minus 1, 3. 2, 1, xk. So how you can use 3 points in order to compute the new point? So from 3 points, you know that the function is differentiable. So if the function is smooth, so essentially we need here that there is at least 2 derivatives, and for the proof you will, I guess, need to have 3 derivatives. But from 3 points you can write a parabola. So you can write a second order polynomial. P of y such that passing through the 3 points that we have. So through x k minus 2 f of x k minus 2, x k minus 1 f of k x k minus 1, and x k f x k. So you can take second order polynomial passing through this point, and then, so it will be something like this. So this is P. And then second order polynomial, we know how to find zeros, right? So we find 0 for this polynomial, and this will be x k plus 1. So certainly we expect that this method is better than this because we use more information. We use better approximation of the function. So it's if the points are close enough to the solution, so this should better approximate the function so that our next guess will be better. So that's natural. And there is a simple way how you find this, how you write the solution explicitly. So that gives us what's called Mueller method. So this is, it's written in terms of, so you write it in terms of first, second order, it's what's called divided difference. So you take the xk minus 1, so it's f of xk minus f of xk minus 1, xk minus minus 1. So this is first order divided difference. And in the same way, in similar way, you can define the second order divided difference. So it will be xk minus 1, minus 2. So this is what? So this is divide difference, but using the previous two. So you use the other two. Okay. 1 minus f minus 2. I think so, like this. So it will be. So this is second order divided difference. And then in terms of these functions, you write the polynomial, and it just has a direct form. So it will be f of xk plus y minus xk by this first term. Plus y minus xk squared xk, and then this second order term is more tricky. So it's, you see, it's two product of the two sequential terms times this divided difference. So you can just check that this is exactly polynomial that we need. So this polynomial, this is just a convenient form to write a polynomial passing for given 3 points. And then you solve the quadratic equation for this polynomial and take the root closest, because there will be two, closest to xk. No, and this gives you the next point. So I'll write you the expression. The expression is, well, so the expression is that new point well, there is not much information in this formula. It's just a solution of the quadratic equation, but just for you to see that what more or less form it takes. So this is a formula, and then what is inside is that lambda k is f divided by wk, then mu k is second order divided difference over also wk, and wk is first order divided difference minus or plus difference by the second order divided difference. Well, just expressions which people put some effort to reduce to some nice method, nice form. So there are two observations about this method. Is that rate of convergence is also fractional, and it's more or less, it's close to 1.83. So you see, it's better than second method. Because for second method, it was golden mean, right? It was something like 1.6, I think 62. But worse than Newton's method. Which has a rate convergence too. So somehow this is, I would say, even surprising, because Newton method has a linear approximation, but taking the derivative right at the point, here we have a quadratic approximation, which is much better than linear, but it uses, but it's not based on derivative, it's used by the previous point, so it gives you certainly better than using two previous points, but still worse than Newton method. Though the difference is not probably that crucial. So essentially, the good part of this method is that we don't need derivatives. So we almost get convergence like Newton methods, but we don't compute derivatives. And for any problem, for any problem which is where f is something very complicated to compute, which usually implies that derivative is just not computable at all in many cases, because it's differentiating is difficult. Then we just use previous. We just make a method which is like Newton in spirit, but using the previous points in order to improve the convergence. And another observation, so another observation is that there is a square root here. And it is because we approximate the function for three previous points by a parabola. And parabola doesn't have to cross the real line, right? Parabola may have no solutions which are real. And in this case, this number will be negative, and then the square root will be imaginary. So it gives you a complex number. So the nice part is it still converges. So this works. So Mueller method works for finding complex roots. So f can be complex function, homomorphic function of complex number, and you just use this method in order to find complex root. And the complexity will come on the way. So if it converge, if you start not so far from a complex root, it will converge to the complex root. Well, I wanted to give you a little more, but no time. So we still have a little bit of the numerical method, but then we'll go, I think, to linear algebra, then we'll go back to solving equations. But well, there's still a lot of information there. So till next week. Thank you. Andre, if you want. So this is Andre. He's your monitor.